So the title of my talk might have made you wonder a little bit. So it's called Building Applications with Next Generation Neuromorphic Hardware. And as many of you know, this is a talk about Loihi and Applied Brain Research's adventure in working with the hardware and putting applications on it. And the reason I thought it might make people wonder is because you probably also know that Loihi is just released. And so the question would be, how do you put applications on hardware which is just released? And that's why I'm actually going to start my talk a little differently today. Instead of sort of just diving into results, which we'll get to eventually, I want to tell you a little bit of a story. And this is going to be our adventures over the last 2 months of working with brand new hardware and trying to figure out how to put applications on them. And so this, it all started about 3 months ago when Mike came to us and was wondering, do we think that there are applications that we could target onto this particular hardware platform? Of course, we didn't really know too much about the hardware platform, but making applications is kind of what we did. And so this was super exciting, right? It was a Christmas present. You get this, what engineer does not want for a Christmas present the latest hardware to come out of Intel, right? It's just super cool. So we were excited about it, and we were thinking, there's all kinds of things we could possibly do, right? Maybe we could put a deep spiking network that could, classify the millions of images in ImageNet on there. This is work that we had done before. Or maybe we could build a controller for a quadcopter, right? So this is a kind of adaptive controller that learns over time with experience as the quadcopter flies around an environment. Or maybe we could put a spawn on there. So this is a great big model. It's now kind of in its second iteration, has about 6.6 million neurons. It can do 12 different tasks, all kinds of interesting things. But of course, there was one enormous constraint, right? And that's that we had 2 months. So as much as we would like to dream about the kinds of things we could do, we also were faced with this reality, which from some perspectives is a lot of time, right? But from other perspectives, it's not really that much time. I mean, there was only one Olympics during that period, but you could have fit 2 in. And from other perspectives, it just seems like almost no time at all. So, a huge challenge. And there were other challenges. So, as I mentioned, this was a brand new piece of hardware. And so you don't get things like this when you're trying to program this kind of hardware, right? So this is a big challenge. We were faced, the API wasn't ready, as you saw. It's still sort of under development. And so we were going to have to do like bare metal programming, which for those of you who don't know, that means you get to go and flip the bits that determine exactly what's going to happen at a particular location in memory. And some of those are control bits, and some of those are data bits, and you have to know the differences. And there's all kinds of optimizations that have gone in. So the bit codes are usually very unintuitive. And so it's a huge challenge. And if you make a mistake, right, you're not told what your mistake was, right? Just kind of nothing happens anymore, right? So we were basically in a situation where we did not have what Hava was asking for yesterday, right, which was like an easy programming language to target the chip. Of course, hopefully there will be one soon, and that's another story. We can talk about that tomorrow. But at this point, we really had some severe challenges and constraints. But nevertheless, we still had the exciting problem in front of us is trying to figure out what kinds of stuff we could do. And so after lots of back and forth and trying to figure out what seemed reasonable, what did ABR have experience with, and so on, we came up with 4 particular application targets. So the first of these is speech processing. So in particular, doing keyword detection, right? So things like, hey Siri and OK Google. We also wanted to try some kinds of reinforcement learning to leverage the learning that's on the chip. So could we have this sort of super cool advantage of being able to actually get the chip to do some learning for us. And we also heard from Intel that they wanted to show industrially relevant applications. And for neuromorphics, this is something that people have been looking for a long time. So of course, we wanted industrial relevant applications as well. So keyword spotting, obviously it's used on all kinds of phones. It actually runs on low-power chips now, so it seems like a pretty good target. There are also things like motor control. And that's the one I'm actually going to spend most of my time talking about, so I'm not going to talk about it right now. And then we also wanted to do some sort of familiar kinds of networks. So we wanted to do a deep neural network, convolutional network, doing image classification. So I'm going to talk a little bit about each of these. And you can come over to the demo room if you haven't already and actually see a bunch of these working. So the first one is the keyword spotting that I mentioned. So this is now working, streaming. So you talk right into the thing, and it will classify in real time whether or not you said aloha. We figured we'd pick a word which is appropriate for Loihi. So this meant that we had to gather all the data. We had to train a deep neural network in order to do that kind of classification, and we had to port that network onto the chip. And we managed to do that with actually fairly good preservation of the accuracy. So you can see in Nengo, that's basically our software simulation of the network. We had about 87% test accuracy, and on Luihi, we had a similar level of accuracy. So that was good, right? Because it meant that we preserved the kinds of functionality that we wanted. Then we also had this reinforcement learning case. So I would challenge anyone to go play this thing, again, in Tic-Tac-Toe. Of course, this is no AlphaGo or anything, but it's playing a nice, simple game, and it will beat you every time or tie you. So far, at least I don't know of anyone who's gone and actually beat the thing. It started out not knowing anything. So here we can see the very, very beginning of the learning, where we set all the weights to 0, and we just started letting it play games of tic-tac-toe. It gets -1 for a loss, 0 for a tie, and +1 for a win. And so you can see that basically that line is trending downwards because it's losing pretty much every game. And it's just playing against a sort of greedy algorithm that's not a very good tic-tac-toe player, but obviously better than what it starts out as. So this is 300 games, and if you do this sort of 10 times, so about 3,000 games later, you end up with performance that looks something like this, where now you can see its win rate is up near 60%. Right? And tic-tac-toe, of course, you should tie most of the time. And the reason there's a win rate here is because it's not playing an optimal other agent. But if you go and play it now, right, it's basically not going to lose any games to you. And so the nice thing about that example is that's leveraging the learning that's right on the chip. And then, of course, we wanted to do this. But this was the one casualty of our 2-month time frame. So we actually built a network that just exactly what could fit on one core. So this is about 84,000 neurons. It was doing CFAR 10, which is a bit simpler than this. And I think that's basically about 2 weeks out from being finished. So hopefully it will be available to people if they want to play with it on Luihi in not too short order. So, we were very happy with all of these. And as I mentioned, I'm going to talk a little bit more about adaptive control. But it also seemed at many points during that 2 months that someone did not want us to actually get this project finished. And I don't really know who it was, but my suspicion, given the things that he said about how AI is the greatest existential threat to humanity, I think it was probably Elon Musk. I don't have really good proof of that, but I'm just going to tell you a couple of the things that happened while we were building up these sorts of applications. So as you know, we're from Canada. Canada's cold. That means there's lots of ice and snow. And some of that ice attacked Terry Stewart, threw him to the ground, and broke his arm. So you might have seen him walking around. He's got a cast still. And so halfway through, we're like, Terry broke his arm. Can he type anymore? Challenge number 1. Challenge number 2 is, we're mostly software people. We don't deal with hardware that much. But they had given us hardware that we had in our headquarters, which is my basement. And when I was basically setting this thing up and getting it going so we could actually talk to it and start playing with it, there was a lot of playing with SD cards, taking them in and out, trying different kinds of operating systems, making sure everything was set up. And it all worked, and it worked for 2 months. And one morning, I went down, and there was absolutely no power to the hardware at all. And I had no idea why. Nothing special had happened that night. So we're in a bit of a panic because, of course, if we don't have the chip, we can't actually be building the applications. We're kind of halfway through. Called up Intel, John C., and told him the thing doesn't work anymore. We tried a little bit of hardware troubleshooting. It really didn't seem like there was much we were going to do, so we sent it back. And we had a downtime of only 2 days, which was actually incredibly short because John got one of those systems right back out to us. When they had a chance to look at it, it seems like someone had put the SD card in maybe a little too many times or something, and something got loose, and eventually it just kind of gave up the ghost. But that was definitely an exciting period. Another sort of more technical challenge is, as I mentioned, the software was very under development, and so we got 4 different runtimes during the course of the 2 months, which was great in some ways because it gave us extra features that we could exploit with some of our applications, but of course it also means that you have to rewrite your code every time that you get one of these in order to deal with the changes. Another challenge that we had was due to a small, beautiful baby girl whose name is Claire Bacoli, and she was born on February 22nd, or February 15th, rather, 2018, and she single-handedly took out half of our speech team. And, all of these things seemed like, the day we were coming, it seemed like we had finally overcome all of these sorts of challenges. And as we were about to get on the van to take us to the airport. We got a phone call that said the van broke down. So we're like, really? They had another car. They brought the car. We all piled in very cozy in a tiny little car with a bunch of suitcases and everything, got ourselves to the airport, and we managed to get here and got everything set up and running. And so that was definitely, I think, qualifies for having an adventure. Right? We had all of these barriers that were thrown up in the way, and we also saw huge amounts of heroics. Right? So we had Terry typing away with a broken arm. We had John sending us that chip with 2 days' notice, and John was also just on call like basically 24 hours a day. Andreas also at Intel's answering my emails all weekend and all the time, trying to help me figure out what all these registers were and how everything would work. We had Pete Blau, who did the speech stuff, who had never done anything in speech before. So I think that as a team, I was just super impressed what everybody did and pulled together to get these applications actually up and running in the way they were. And Paweł Jaworski had to sit with me for 6 weeks in a basement, so that's also pretty impressive. So at the end of that adventure, I think one of the more significant applications that we've developed is one that's related to motor control. So if you've been in the demo room, you've probably seen that robot arm moving around. And that is basically what I'm talking about today, is how do you build a system that actually demonstrates that the neuromorphic hardware is giving you an advantage that you would not otherwise get. So first, what I'm going to do is sort of set up what the application is, the kind of problem that we're trying to solve, and then I'm going to speak very directly to that and show you some data on why we think we've got something pretty interesting. So motor control is something that people do, and do it incredibly fluidly and elegantly, and do it incredibly quickly. It's a very challenging problem because of the timing constraints. It's very sensitive to changes in dynamics. And right here, we see a tennis player who's basically tracking a ball and is trying to line up his arm with this mass that's in his hand that has a very weird mass distribution, but it's one he's got a lot of experience with. So he can figure out exactly how to apply forces on his arm in order to get it to the location of that quickly moving object. And one of the things that people are really good at is actually adapting to those changes in the mass that's at the end of the arm. Right? So in the case of the tennis racket, he's got tons of experience. But you can also give people tools that they might never have used before. Maybe they've used a hammer, but not this particular hammer, so the mass distribution is different. And after a little while, maybe missing a couple of nails, people will become pretty accurate. And you can have huge differences between tools, right? So you can have a massive hammer, you can have a very light screwdriver. And those changes significantly affect the dynamics of the system that is under control. And that has to be taken into account. And it's the kind of thing that you really want to be able to change online because you don't know in advance the shape and mass distribution of every tool that you might run into. So the system is very good at dealing with these variable nonlinear dynamics and exhibits fast adaptation. There's another kind of adaptation in the motor system as well, and this is kind of more related to kinematics. So basically the plant, the system that is being controlled by the controller, significantly changes. It tends to change a little bit more slowly, right? So as we grow up, we are using the same controllers, the same brain that's learning how to control us. Using and controlling our limbs as they change. There's those awkward teenage years, which basically is when the controller is struggling a little bit to keep up with the changes in the kinematics. But nevertheless, this kind of adaptation is also important, but it tends to be a kind of much slower adaptation. So let me put this now in the context of something like much more specific, and that's basically reaching an arm to a target, right? And so this is the kind of thing that we're interested in with that robot that you may have seen in the demo room. So to set up this task, we can identify the position of our end effector with this variable x. So this is a vector in 3 space. And there's some kind of target that we're trying to move that end effector to, x star, also in 3 space. Right? And so I'm going to call that the task space, or it's sometimes called the operational space. And this is kind of sort of the intuitive space that we think about motor control in. Right? My arm starts here, I'm trying to get to a target, and I move. Right? So I can think about the vector between those two as the path that is being followed. But of course, that's not what the body is doing, right? The body is not putting a force here directly, right? Instead, we have these effectors, we have joints, which I'm calling Q, right? And in this joint space, we have to figure out how to actually, change the torques on those joints in order to have that nice straight line occur in the task space. And so there's this distinction between the joint space and the task space, and one of the things that the brain seems important for is figuring out how to do that mapping between the two. And so as a controller, right, so I've just sort of drawn some parts of the motor system, which I'm talking about here. The brain has to figure out how to generate that control signal U, right? So this is a set of torques that are going to be going to each of the Q in order to solve the task of getting x to x star. All right, so if we look in the brain, people have done all kinds of interesting research to discover what kinds of representations seem to be sitting where, what parts of the brains are involved in what parts of this computation. And the representation in the task space of the target often seems to be related to the premotor cortex, which I've circled in blue. So here we can think, in this model that I'm talking about, we've called reach. So the reach model assigns the representation of that task, of the target in task space to the premotor cortex. And some evidence for this is that if you actually sign your name with your foot, which is not something people do a lot, but if you do that, it actually looks kind of like when you sign your name with your hand. And that suggests that there's this representation which is somewhat independent of the part of the body that you're using to solve the task and follow a path. And that seems to be related to activity in premotor cortex. So the simplest kind of controller that we can have and we can define in the task space is basically just to move from where we are to where we want to go. And this is a simple proportional controller. And so we can define the control problem up on the top right. My laser pointer gets lost on the screen, so I'm just going to have to hope you can follow along. So we define in the task right, we have a proportional controller, the difference between where I am and where I want to go, and we multiply that by some gain, right? This is the p term in a standard linear controller. So that's a good start. But we actually have to relate that to the joint positions as well. And we need to be able to figure out how do all those joint positions and their masses and everything map from that x space, from the task space, so that's u sub x, into the space that we're actually controlling, which is u. Okay? And we think that that kind of mapping seems to be one of the primary concerns of motor cortex, primary motor cortex. We also have to deal with all kinds of sort of additional forces, like Coriolis forces and so on. This is what introduces a lot of the nonlinearity in the motor system. It seems that the cerebellum is central and critical for doing that kind of control. In the terms of a simple linear controller, this is your d term, your derivative term. And so again, we have a gain, kv, which is just multiplying your q dot. So now we're looking into the actual arm space. And we're mapping that through this mass matrix as well, because that's the thing that actually determines what kinds of forces are generated as you're moving with velocities in that space. So that, again, that we don't have to do any kind of translation for, because it's actually in the same space. It's in the Q space as the actual control signal that we're trying to generate. So we can add that into our controller. And then lastly, there's all the stuff that we don't know, right? So far what we've really done is essentially develop a linear controller. And it's a linear controller that's mapping between two spaces. But we know that the arm has all kinds of nonlinear effects. And there's all kinds of uncertainties, things that we don't really know about. And we can put on this adaptation term, right? So that's the thing which is essentially going to be taken care of when I have a hammer as opposed to no hammer, right? It's got to adapt to the changes in the dynamics. And it can also account for other things which are not captured by my linear model. So taken together, we can generate our entire control signal by mapping our sort of simple controller down into the joint space from the control space, from the operational space. We can account for some of the kinds of dynamics that we expect in the velocities directly in that space, and then we can add an additional term which is going to account for the basically uncertainties and all kinds of nonlinearities and so on that are going on. And one thing that I'll point out here is that that last thing you adapt can be really complicated, right? So we know that cerebellum has about as many neurons in it as there are in all of cortex. And they seem to be organized in very regular structure, exactly the kind of structure that you'd want if you were trying to fit very complicated nonlinear functions. So when I was talking about those two kinds of adaptation before, so the reach model actually includes both kinds of adaptation. I'm really going to focus on dynamics adaptation. But the slow adaptation basically is related to that mapping, right? How do I go from my operational or task space to my joint space? That's the thing that changes as my size of my arm actually changes over time. And so we can account for that by looking at that term and actually trying to update and adapt the Jacobian. The rapid adaptation, which I'm going to focus on, is something that seems to be more related to the kind of activity you find in cerebellum. And so you can think of a lot of this adaptation, or basically the simple neural network that we're going to build to account for these changes that are unexpected, to be a very, very simple model of what's going on inside the cerebellum, right? And trying to account for these extra additional nonlinear effects. OK, so the model that I showed you is one that we've had around for a while now. It was Travis de Wolf's PhD thesis in my lab, and he's now working for applied brain research. And when he first built it, he wanted to do a nice solid comparison to a bunch of other kinds of optimal controllers and so on that you see. And what I'm showing here is kind of trying to quantify what the differences are between the two across 4 different tasks. And you can see that the reach controller seems to be doing reasonably well. It's doing the best kind of overall and very comparable to the OSC. But there's a huge difference between OSC and reach, and that is basically the adaptation term. Right? And so one of the things that really isn't captured by this kind of quantification is actually looking at the different kinds of movement. So on the right side, you see the reach model after training, right? And it looks like it's making nice straight line reaches, which is what it should be doing. And on the left, you see the kind of performance that you get of LQR, which even though the numbers look okay, the performance is actually pretty terrible. Right? It's really not usable in many kinds of ways. And the same sort of thing is going to happen to the OSC if you begin to give it sort of unknown nonlinear forces. We can also look at the efficiency. So what is the computational cost of these different kinds of algorithms? And here we're comparing reach implemented in a spiking neural network to sort of standard implementations, algebraic implementations of the other ones. A lot of these, so things like ILQG, you just would never implement in a neural network because it's way too computationally costly. But the thing that is interesting here is that we notice as we scale up more complicated degrees of freedom, we actually get a significant improvement. So this is a log scale on the left side. We get a significant advantage using this kind of reach adaptive controller as opposed to these other sorts of control. OK. So I'm actually going to skip this movie because I was just told I have 5 minutes left. And this is almost 5 minutes. This is essentially introducing different kinds of control, comparing and contrasting sort of industrial control with compliant control with the adaptive compliant control. If you want to see this stuff live, then please come to the demo room. The one thing I'll focus your attention on is the spiking activity in the left side here, the bottom left side. And this is a demo that we originally developed for Intel just to give them a sense of what kinds of things could you do with spikes. But here, all the spikes are simulated in software. Right, so the challenges that we had in trying to map this onto Loihi is that we wanted to demonstrate that we could. Right, so can we actually get this working in spiking hardware? We want to demonstrate that it's better than other kinds of solutions that you'd have for the same sort of problem, this control problem. So the most common thing that is found in industry is PID control. So this is a linear controller. It'd be nice to demonstrate an actually industrially relevant result. So is this something you could go to industry and say, look, you should use this controller because X. And then lastly, it would be even better if we could demonstrate that the result depends on having that adaptation, having that UAdapt actually running in hardware as opposed to being simulated in software, because we know we could, of course, simulate it in software. All right, so let me show you the results. So this is going to be a single reach, 5 trials, 50 runs. This is the baseline performance. Here, the error is basically compared to the ideal movement of a mass of the same size. So we know, what is the optimal trajectory, and so we can see it's not optimal, but it's doing okay. So this PD baseline is basically we basically have a nicely tuned PD controller, and then we give it a mass that it doesn't know about, and then it's trying to move to the target, right? And so you get this error, and you get very constant error because, of course, it's not improving itself in any way. If you add in the I term, right? So this is the integral term, and it's basically there in a linear controller to account for this overshoot kinds of errors that you tend to get. You can see that it can actually improve the control, right? So you actually can do better than what you did with the standard PD controller, which is great, right, and expected. However, if you add in neurons and the adaptive component, you can actually do better. So what we're doing here is we're actually saving the weights between each run, right? So it's getting better and better slowly over time, but then doing the same sort of thing. And we see a significant improvement. I'm running on a simulator, so on the Nango simulator, so this is in software. And if we take exactly the same thing and put it in hardware, we find an even better improvement, right? And the reason that we think we're getting that better improvement is because when you're running anything on the CPU, you are basically slowing it down. This kind of control is very sensitive to delays, and you basically increase the delay when you get the CPU to do more work in the same length of time. OK, so that's an OK result, but really PID can deal with sort of unexpected perturbations to some degree when you're making a single reach, but it can't deal with nonlinearities, right? And so what we're doing here is introducing something that is a real industrial concern, and that is that you have friction in all of the joints. Here we've got this Strybeck model of friction, so this includes the sort of 3 standard kinds of friction that you'd expect, viscous and so on. And it gives you this sort of strange looking curve, clearly a nonlinear one. And it's something that, if you're using your robot over and over in a manufacturing environment, you actually have to go in and retune it all the time because you're increasing the amount of wear and tear on them, and the amount of friction is actually increasing significantly. And so what we're doing here is we're showing what happens if I take a robot and get it to move, and then I apply what would be sort of 3 years worth of friction. So if I used it for 3 years and then I wanted to keep using the robot with the same controller. Same sort of setup. So here's our baseline, right? This is sort of how PD worked with no friction at all, right? This is how we started. Then we add friction to PD and we get this big jump. And so we're calling that difference 100% error. Right, so we get 100% error, which means that the PD controller, basically, that's going to be the worst kind of thing we would expect. And this is after 3 years of friction. If we look at PID, we actually see it get worse. Right? And this might seem a little bit puzzling because it's supposed to account for the kinds of changes you expect. But in fact, what's going on is it's trying to average across this weird nonlinear function in many different parts of a space. And so it's accumulating error instead of actually reducing the amount of error because of the nonlinearity it's trying to deal with. If we run this again with 1,000 neurons on Nengo, we see that we get a nice improvement. So it can actually, over these 50 trials, it can get back down to the original performance level. And if we do the same thing on Loihi, then we get the same kind of improvement, which is great. So far I've shown you that adaptive control is good. It actually solves a real industrially relevant problem. But I haven't shown why we would care for it to be in hardware. I've just shown that the hardware is doing as well as the software. So one more result for you. So this we're going to call accelerated wear simulation. So instead of just jumping to the sort of 3-year wear, for every single run, we're going to increase the wear a little bit until it gets up to the 3-year level, and we're going to do that linearly. So we're going to make it sort of progressively more difficult. So it's kind of like accelerating what a robot would actually have to deal with. So again, we start with these 2 reference lines. So that's sort of PD with no friction at all, PD with 3 years of friction. And then if we just gradually introduce it, we see that actually PD gets bad very quickly. It gets up to its sort of worst performance level and then kind of stays there and sort of just drifts a little bit at the end. If we run Nengo on Loihi with 1,000 neurons, right, we see that it does better for longer, but eventually it drifts up and basically about halfway through it becomes a little bit unusual. We're getting over 50% error. So that's running on hardware with 1,000 neurons. But if we crank that up to 20,000 neurons, which again, we're only using 1/6 of which actually on one chip, then we can pull that way down, right? So now, with more neurons, we've doubled or tripled the length of time that we can run this thing before we'd have to worry about going in and tuning it, right? And so this, again, is the kind of thing where if you can do less maintenance, right, you can get people pretty interested and excited about that. And lastly, you want to ask the question, well, just a minute, what about running it in software on Nengo? So we can also plot that, and it gets terrible. Why is it terrible? Because now it's trying to run 20,000 neurons on a CPU. It's slowing everything down, right? And you've just introduced a big delay. You go from like 3 milliseconds up to 5 millisecond delay, and that is killing your performance in this task now. Right? So this is, to me, this is exactly the kind of story that we wanted to tell. Right, it's one where we see that the hardware is playing an essential role. You only get the performance on the hardware. And it's showing application to an industrially relevant sort of problem. And then just for icing on the cake, yesterday, right, we got here and we actually got power measurements on these sorts of things. Because, of course, this is one of the things that we also want to ask ourselves. What is the power differences? So in this case, we're comparing 20,000 neurons running on the CPU versus running on Loihi. So we know that the CPU isn't actually doing what we want, but in any case, we can ask, how much power is it taking? And we get a 36-time improvement on Loihi, right? So a huge drop in power. We can ask the same question for something like speech, right? This is one that we really, would like to be low power. So here, there's no learning on the chip, right? But we are using sparsified representations over time, and so you get way less sort of information sent per time slice of the audio signal on what you're doing classification, but we saw that the classification levels were comparable. And here we get a 47 times improvement in the power usage, right? So exactly the kind of thing that we were hoping for, but this is like super fresh off the press. We just got these results yesterday. All right, so I'll skip this slide. I'm getting the stand up, but I will do my last slide, which is just trying to step back a little bit, right? And I want to sort of remind you what I talked about last year. So I gave a talk last year, and I talked about this, right? Like trying to take neuromorphic technology and neuromorphic applications and make them real, right? And I harped on 3 things, right? Scaling, I thought, was really critical, and scaling and scaling, right? So I really think that there's all kinds of examples that we have in the neuromorphic community where we can build sort of small networks and we can show that they can do something, and sometimes they're optimal, sometimes they're not, but we can get them to do something. But what we really needed to do is figure out how to push things upwards and make them industrially relevant, make people outside think that neuromorphics really is a way to do AI, right? So one of these is to scale complexity. So I showed you an example of 20,000 neurons, but the example which will be out in a week had 84,000 neurons, right? So these are now pushing pretty good sizes of networks running on chip. Generality, we've showed how you can take deep learning, put it on the chip, reinforcement learning on the chip, adaptive control on the chip, right? Audio processing on the chip, visual processing. So again, we're showing that this platform is enabling us to solve a huge variety of problems. And then lastly, actually finding applications which we think are industrially relevant, where we can go and make head-to-head comparisons and say that this neuromorphic solution is really the best solution for the problem that you as an industry, manufacturing industry, who doesn't really care about AI, right? But you do care about doing the problem as well as you can, and we get this extra bonus that's going to be low power, right? That's exactly the kind of thing you want to be able to say. So I think the race is on, essentially. So we know that there's low-power GPUs out there, mobile GPUs. There's trying to solve some of the same sorts of problems. There's different strengths and weaknesses. But right now, I think it's really exciting because we've got to the point where I was hoping we would be last year. I remember talking to a reporter right after my talk, and he's like, how long before you think you're going to have these neuromorphic chips around? And I said, well, for people to actually use. And I said, well, 3 to 5 years. And he thought I was nuts, right? But at this point, I think that's a much more plausible answer than what he thought at the time. And it's, I just think it's a really exciting time to be involved in this and building these sorts of applications. And so I really think the adventure is just really getting started, right? And see where it goes next. Thanks.
So we'll do one question while we set up the next speaker.
So even if I didn't know that you had just 2 months and your challenges, but still all the demos that you guys showed is really awesome. So your team definitely needs a big hands for that.
Yeah, that's very kind.
So, okay, so I have a question about the Tic-Tac-Toe game. So, so in that game, actually, you used a pre-trained RL model, and you made a spiking representation, loaded into Loihi, and ran in real time the spiking neural net, right?
No. So we actually learned the entire RL model on the chip.
So
we started with, so we basically have the state of the board, and we project that through, turn it into spikes, essentially, send it onto the chip. And we have a learning rule on the chip, and we have the Q values at the current time, and in sort of the next step, we generate an error signal from that, put that on the chip, and then the learning occurs on the chip, so it updates all the weights. And then we do that over and over and over again, and it becomes this good learner. So the learning is actually all happening on the chip.
So did you compare with the deep RL model, or you did only the entire learning on the chip?
Yeah, we just did all the learning on the chip. And we we compared it, so the way that a lot of this development progresses is by building the software implementation and making sure that it's going to work, we expect it to, and then comparing those results to what we're getting out of Loihi. And when we have the same kinds of constraints on the software model and on Loihi, we're getting very similar results.
Yeah, okay. So my quick question then is, if we actually do that, if you use a pre-trained model on Loihi,
so we did that for
easy
speech.
it is, or what are the challenges or your insights?
Okay, yeah, sure. So that is the strategy that we took for the speech model. So that was a deep neural network, and we had to sort of pre-collect all of the speech data. And so in that case, we trained a model offline. We then converted that model. So at ABR, we have these methods for taking standard deep networks and converting them into spiking neural networks with similar performance for the same number of neurons. So we use those to generate a software model. Then we can take that software model and impose the constraints that are consistent with what you have on Loihi, so things like 8-bit weights and so on. We can then ensure that that simulation works basically as well as the non-spiking version, and then map that into the chip. Yeah. Thanks.
Thank you, Chris.